Hey, welcome to your own personal deep dive.
Yeah.
Today we're going microscopic, exploring how osmosis and membrane transport
Oh, cool.
actually work inside your body. We're
Awesome.
talking about how your cells get what they need
Right.
and stay in balance. You ready to get a little
Yeah,
cellular perspective?
absolutely.
Uh-huh.
It's fascinating how these processes
Yeah.
happening at such a tiny scale have such huge impacts on our overall health.
Right.
Yeah.
And get this, we'll uncover why salt messes with your cells way more than sugar does.
Huh.
It all comes down to how water moves around, and trust me, it's way more exciting than it sounds.
It really is.
Huh?
To kick things off, let's clarify two key concepts:
Okay.
molar concentration and osmolarity. You can think of molar concentration like measuring how much of something is dissolved
Right.
in a liquid.
Yeah.
Imagine making lemonade a higher molar concentration means you've got a seriously sweet lemony drink.
Okay. That makes sense.
Yeah.
But how is osmolarity different?
Osmolarity adds a layer of complexity.
Okay.
It considers how many particles a substance breaks down into
Right.
when it dissolves.
Yeah.
So even if you have the same molar concentration
Oh,
of two different substances,
yeah.
their osmolarity can be different
Okay.
if they break apart differently in the solution.
Hold on. Could you give me an example? That sounds a little tricky.
Sure, think about salt, which is sodium chloride.
Okay.
When you dissolve salt in water,
Right.
it breaks apart into two particles, a sodium ion and a chloride ion. So a 1 molar solution of salt actually has double the osmolarity
Okay.
because of those two particles.
Ah, okay. So it's not just about how much stuff is dissolved,
Right.
but also how much that stuff breaks apart in the liquid.
Yeah.
That makes sense why salt would have a bigger impact than sugar. Sugar doesn't break apart like that, right?
Exactly. A 1 molar solution of glucose, a type of sugar,
Right.
would have the same osmolarity.
Okay.
It stays as one whole molecule in solution. This difference in osmolarity is super important when we talk about osmotic pressure,
Okay.
which is essentially the force behind water movement across cell membranes.
Okay. Osmotic pressure. Now we're getting to the good stuff. I'm picturing a cellular tug of war.
That's a great way to visualize it.
Uh-huh.
Imagine a cell membrane separating two areas with different solute concentrations.
Okay.
Water will naturally move across that membrane to try and even things out.
Okay.
It flows from the area of lower solute concentration to the area of higher concentration,
Okay.
almost like it's trying to dilute the side with more stuff in it.
So the greater the difference in those concentrations, the stronger that pull, that osmotic pressure.
Precisely.
Yep.
It's similar to how gas pressure works.
Okay.
But instead of gas molecules bouncing around, we have water molecules trying to create a balance on both sides of the membrane.
Right.
And this pressure is vital for so many things, keeping our cells hydrated, moving nutrients, even filtering waste.
Wow. So this is happening all the time inside our bodies.
It is.
I never really thought about water being such an active player at the cellular level.
It's essential.
Hmm.
Speaking of water moving in and out of cells, this makes me think about
Yeah.
those terms I always hear. Hypotonic, hypertonic, isotonic. Could you break those down for me?
Yes, please. Okay. Those terms always make me think of my high school biology class,
Right,
but I could definitely use a refresher.
of course. These terms describe the relative solute concentrations of two solutions separated by a membrane.
Okay.
Let's start with what happens to a cell
Okay.
placed in a hypotonic solution.
Okay, let's dive in. What does hypotonic even mean?
A hypotonic solution has a lower solute concentration compared to the cell itself.
Right.
Since water wants to move where there's more stuff dissolved,
Yeah.
it rushes into the cell to try and balance things out.
So the cell would swell up like a water balloon.
Exactly.
Hmm.
Now imagine the opposite scenario, a hypertonic solution.
Oh.
In this case, the solution outside the cell has a higher concentration of solutes.
So water would rush out of the cell.
Leak and it shrivel up.
Exactly.
Ouch. I can imagine that wouldn't be good.
You're right. Cells need to maintain a certain volume to function properly. That's where isotonic solutions come in.
Okay.
They have the same solute concentration as the cell, so there's no net movement of water. Everything stays balanced.
So isotonic is like the Goldilocks
Mhm.
solution just right.
Uh-huh. Exactly.
You know, I once learned about hypotonic solutions the hard way.
Oh, really?
I chugged a whole bottle of water after a workout
Yeah, I've done that.
and felt incredibly bloated. Turns out I overloaded my system.
Oh, wow.
It's amazing how our bodies are constantly working to maintain this delicate balance.
That's a great example of
Yeah.
how these concepts play out in our everyday lives. And you're right, our bodies are constantly working to maintain that equilibrium.
This is already making me rethink how I approach hydration.
Yeah,
So we've covered molarity, osmolarity, osmotic pressure,
right.
and how different solutions affect our cells. Where do we go from here? Well, there's a fascinating law that helps us quantify osmotic pressure. It's called Van Hoff's law.
Okay.
And it gives us a mathematical way to understand the relationship between solute concentration, temperature,
Okay.
and osmotic pressure.
Ooh, a law.
Yeah.
Now it's getting serious. Tell me more.
Van Hoff's law might sound intimidating,
Right.
but it boils down to a simple idea.
Okay.
The higher the concentration of solutes, the higher the osmotic pressure.
Okay.
It's like adding more and more air to a balloon, the pressure inside increases.
So if you have a really concentrated solution,
Right.
the osmotic pressure will be high
Exactly.
because there's a stronger drive for water to move in and balance things out.
Exactly. And the law also shows that temperature plays a role.
Okay.
Higher temperatures mean molecules move faster, leading to a higher osmotic pressure.
Right.
It's like heating up that balloon.
Okay.
The air molecules inside get more energetic and bump around more,
Yeah.
increasing the pressure even further.
Okay, I'm starting to see how all these pieces connect. But I'm also realizing that we've mostly been talking about water moving across membranes.
Right.
What about all the other stuff our cells need, like nutrients and waste products? How do they get in and out?
That's a great question.
Yeah.
And it leads us to another important concept, filtration flow.
Okay.
It's a process driven by pressure differences across membranes.
Okay.
And it's how our bodies move fluids and all those important molecules you mentioned.
Okay, I'm intrigued. Tell me more about this filtration flow.
Think about our blood vessels as a network of pipes
Okay.
with tiny little filters built into the walls.
Right.
These filters, or pores, allow water and small molecules to pass through, but larger molecules, like proteins, stay put.
So it's like a selective gatekeeper
That.
letting certain things in and out.
Precisely. And the movement of fluids and small molecules through these pores is driven by two main forces, hydrostatic pressure
Okay.
and the osmotic pressure we've already discussed.
Wait, so both of these pressures are involved in filtration flow?
Absolutely. Hydrostatic pressure is the force exerted by a fluid, like blood, against the walls of its container.
Right.
In this case, the blood vessels.
Okay.
It's like the pressure you feel when you hold a water balloon. The water inside is pushing outward against the balloon's skin.
Okay, so the blood flowing through our vessels creates hydrostatic pressure,
Yes.
which pushes things out through those tiny pores.
You got it. But remember, we also have osmotic pressure working in the opposite direction, pulling water back in.
Right.
So it's a bit of a balancing act between these two forces that determines the overall movement of fluids and molecules.
This is starting to feel like a cellular traffic jam, things being pushed and pulled in different directions. How does our body keep it all straight?
It's a complex interplay of pressures and concentrations,
Yeah.
but it's remarkably efficient. The net movement of water and small molecules depends on the balance between hydrostatic and osmotic pressure and the permeability of the membrane itself, how easily things can pass through.
It makes me think about those times when you can see the veins in your arms really clearly. Is that hydrostatic pressure at work?
You're on the right track.
Okay.
It can be related to changes in both hydrostatic and osmotic pressure
Okay.
and how that affects the fluids within those blood vessels and surrounding tissues.
Wow. So even something as simple as seeing veins
Yeah,
can be tied back to these processes.
exactly.
It really shows how crucial this balance is for our bodies.
It's a constant and dynamic process happening at every moment in every cell and tissue. And when things go wrong,
Right.
it can lead to a whole range of health issues. For example, if the hydrostatic pressure in your blood vessels gets too high,
Okay.
it can strain your heart and contribute to cardiovascular problems.
So understanding these concepts isn't just about textbook knowledge.
Right.
It can actually help us understand our health better.
Exactly. It gives us a deeper appreciation for the interconnectedness of our bodies and how even seemingly small imbalances can have significant consequences.
This is definitely making me rethink my next salty snack. Speaking of those real-world connections, can you give me an example of how osmotic pressure impacts things outside of our bodies?
Absolutely. Have you ever noticed how sprinkling salt on sliced cucumbers
Oh, yeah.
or eggplant makes them release water?
Yes.
That's osmotic pressure in action.
Hmm.
The salt creates a hypertonic environment around the vegetables,
Right.
causing water to move out of their cells and onto the cutting board.
That's a great example. I always wondered why cooks did that,
Yeah.
but I never connected it to osmosis.
It's amazing how these processes are happening all around us.
It is.
So we've explored these key concepts from the basics of molarity and osmolarity to the forces of osmotic and hydrostatic pressure. But I'm curious, where does filtration flow fit into the big picture?
Okay.
Why is it so important for our bodies?
Filtration flow is absolutely vital.
Because it's the foundation of many essential processes,
Okay.
from filtering our blood in the kidneys to delivering nutrients to our cells.
Okay, now we're talking about the really important stuff and ready to connect the dots. So filtration flow is like the delivery system for our bodies.
Exactly. Think of it as a complex network of waterways,
Right.
constantly moving essential cargo water, nutrients, oxygen to every cell. And at the same time, it's removing waste products, keeping our internal environment clean and functioning.
Wow, that's an amazing image, like a microscopic version of those intricate canals they have in Venice. But what happens if this system gets disrupted?
That's when things can go wrong.
Right.
If the balance of those pressures, we talked about hydrostatic and osmotic, that's thrown off, it can lead to problems. Think about swelling in your legs or ankles.
Oh, okay.
That can be a sign that your body isn't properly regulating those pressures.
Okay.
And fluid is building up in the tissues.
So those seemingly abstract concepts we discussed earlier have very real consequences for our health.
Absolutely. And understanding these principles can empower you to take better care of yourself.
Right.
For example, knowing that high salt intake can increase your blood pressure by affecting osmotic pressure might make you think twice about that extra salty snack.
It definitely makes me want to pay more attention to what I'm eating and drinking. This deep dive has been a real eye-opener.
Yeah.
We started with some basic chemistry terms, but now we're talking about how our bodies actually function at a microscopic level.
It's fascinating, isn't it? And we've only scratched the surface.
Right.
There's so much more to explore when it comes to osmosis and membrane transport. For example, did you know that these processes are crucial for how our kidneys filter waste products from our blood?
Wow, no, I didn't realize that. It seems like every time I learn something new about the human body, it just gets more amazing.
It really does. The human body is a remarkable machine with countless intricate systems working together in perfect harmony. And understanding those systems, even at a basic level, can give you a much deeper appreciation for how it all works.
Well said. This has been an incredible journey into the world of cells and fluids. I feel like I've gained a whole new level of understanding of how my body works and why it's so important to maintain that delicate balance we talked about.
I'm glad to hear that.
Yeah.
Remember, your body is constantly working to maintain that equilibrium.
Right.
Every time you drink water, eat a meal, or even sweat, these processes are at play.
Wow.
So the next time you reach for that glass of water or sprinkle salt on your food, think about the incredible cellular dance happening inside you.
I definitely will. Huge thanks to you for guiding us through this fascinating world of osmosis and membrane transport. It's been a truly illuminating experience.
The pleasure was all mine. Until next time, keep exploring, keep questioning, and never stop learning about the wonders of your own body.
And to all our listeners out there, thanks for joining us on this deep dive. We hope you learned something new and maybe even discovered a newfound fascination with the world of biology. Until next time, stay curious.